What's up, all you badass mathematicians? So today we're going to continue on with some more examples for limits, but more looking at the algebraic form of these functions. So let's look at our first example. For all of these examples, we're going to be wanting to look at the limit as x approaches 0 of f of x. And so here I lay out three different functions that I think will help us explore the idea of limits some more. So something tempting that I think a lot of people try and do, and can be a useful tool, is to try and directly plug in the value that we're interested in into our function. So, and this is actually going to work in a lot of cases, but we have to be careful in the cases where it won't work. So in this case, the limit as x approaches 0 of f of x is actually going to be equal to f of 0, which is equal to 0 squared is 0. So our limit here is 0, and it's actually equal to the value of the function itself at 0. So let's try and graph this just to double check our conclusion. So our graph here is going to look something like this. And we can see that the best strategy here is actually to go from the right and left as per our definition of the limit. So it seems that it checks out that as we approach from the right, we're approaching our f of 0 value, and when we're approaching from the left, we're also still approaching the value of 0. So graphically, this also checks out, and it seemed that actually plugging in for the value was our limit itself. But we have to be careful, because back to our idea of a limit, we're not actually concerned with our value at 0, but rather we're worried about what's happening around 0 from all directions, the right and the left, and we want to see if those values agree. So sometimes the actual value itself will agree with the limit, but other times, we'll see in our next example, this won't necessarily be the case. So moving on to our next example, we're trying to find a limit as x approaches 0 of f of x. Now, if we wanted to say that this is equal to f of 0, well, let's look at our function. So this is a piecewise function, which means the function is going to be defined by different behaviors at different x values on the domain. So this function is defined by x squared when x is not equal to 0, and it's defined by 5 when x is equal to 0. So in this case, if we were to just blindly plug in our value, then we'd get that the limit as x approaches 0 of f of x is equal to 5. So let's graph this just to double check our conclusion. So when x is equal to 0, we're going to get a y value of 5. And when x is not equal to 0, we're just going to have our function x squared. So it looks something like this. And we'll go ahead and put a hole right here just to make it clear that our value at 0 is actually defined by 5 and not 0. So as we can see graphically, when we approach from the right, our value seems to be tending towards 0. And when we approach from the left, our value also seems to be approaching 0. So this is where we have to be careful, because our value isn't agreeing with what our right hand and left hand limits are indicating. So this is a property of a non-continuous function. So this is actually an example of when it's not equal to f of 0. So the more correct approach here is actually, what's the limit as x approaches 0 from the right of f of x? So what's happening? Actually, let's make a table for this. So here's our x values, and here's our values of f of x. So this is going to represent the right-hand limit. So that's what this table is going to represent here. So when we're approaching from the right, let's say we start with a value of 1, and our f of 1 is going to be 1 squared. But remember, we're trying to approach 0, so 1 is way too far away from 0 to actually really be relevant here. So we want to keep getting closer and closer to 0 while still staying positive. So what happens when we plug in 0.1? Okay, so 0.1 squared is 0.01. Well, 0.1 is still too big. It's way too far away from our value of 0. So let's pick an even smaller number that's still positive, 0.01. What happens when you do 0.01 squared? I think that would be 1, 2, 3. And then we can keep playing this game. If I give you a value, you should give me an even smaller value that's still approaching 0 from the right. So you'll say, wait, but 0.01 is way too large of a number. I can give you even a smaller one to check the behavior. 0.001. And I don't know how many zeros it will be, but I think we can see the trend. The important thing isn't any single one of these entries. The more important thing is comparing what's happening as we're getting smaller and smaller, approaching our value of interest. So as we see our x values approaching 0 from the right, our y values are also actually approaching 0. So this is equal to 0. And remember, the limit only exists if our right hand and left hand limits actually agree. And that value is finite, because they can still agree to be infinity but still not exist. So they have to agree on a finite number. So now let's calculate the limit from the left. So we'll do a similar table here, but for the minus. Here's x, and here's f of x. So maybe let's start with -1, and we're going to get 1. And then we want to keep picking smaller and smaller numbers to see what the general trend is. So this method isn't going to be precise, but it will just give you an idea that can be helpful in confirming your intuition and deducing what the limit actually ends up being. So this is 0.01, negative. And the idea here is that when we square anything, it's just going to be the positive version. So we're actually going to have the same kind of table with the negative values, because our function is x squared when x isn't 0. So we see that this is equal to 0. And now we see that our left hand and right hand limits agree on a finite value, and that value is 0. So we can finally conclude that the limit as x approaches 0 of f of x is equal to 0. So notice that the only difference between a and b is our value at 0 are different. In a, we have a continuous function, and b, our function is not continuous. Yet the limit actually agreed. So what we can conclude from these two examples is that you have to be careful when you just blindly plug in the value, because sometimes that won't actually give you your limit, and you should always go back to actually checking the right hand limit and the left hand limit and whether or not they agree on a finite value. So in both of these cases, the behavior of the function around 0 is the same. The only difference being that the value at 0 is actually different. So now we're going to look at our last example today, 1 over x squared. So we want the limit as x approaches 0 of f of x. And so maybe we're tempted to plug in f of 0. And we get 1 over 0. Oh no. So from if you were to type this into your calculator, this would give you undefined. So in math, we don't actually have a notion of what it means to divide by 0. And this should also put some alarm bells in that wait a minute. 0 actually might not even be in the domain of this function, because when you plug it in, you actually get this poorly defined fraction. So in this case, you also can't just plug in, because 0 isn't even in the domain of the function. So we have to go back to figuring out whether or not the right-hand limit and left-hand limit agree. So right-hand limit of f of x. Okay. And then we're going to do the limit as x approaches 0 from the left of f of x. And we ultimately want to see if these agree on some finite value. So let's try our table approach again. So let's start out at 1. So 1 over 1 squared is 1. Well, this value isn't nearly close enough to 0, so we need to get closer from the right. So 1 over 0.04 is 1 over 100th is 100. 0.01. Okay, this is gonna get a little trickier. 1 over 10,000. 1 over 10,000 is 10,000. And that's as far as I'll go. Ideally, we're going to keep wanting to get smaller until we can pick up on a pattern. And the pattern that I'm recognizing here is that we're always dividing by a smaller fraction. Like here, we do 1 over 100. Here, we're doing 1 over 10,000. So then our denominator is going to keep getting smaller and smaller, which actually means that our numerator is getting larger. And since our x squared is on the bottom, we actually know that when we plug in the negative versions of these values, we're going to keep getting the same result as when we plug in the negative values. So this is 100. I really should have had a calculator ready, because these numbers actually might be off. But I think I got it. So what we're recognizing here is that our growth is actually going to keep getting larger and larger as our value approaches 0, whether or not we're going from the right or left. So in this case, it's actually going to infinity, because anytime I give you a small number like 1 over 100, you can give me an even smaller number, and this even smaller number is going to get squared, making it smaller, and it's going to be in the denominator, meaning our actual overall value is getting larger and larger as our x value is getting closer and closer to 0. And this is happening whether or not we're approaching from the right or approaching from the left. And this is also a good chance to graph this function and see if the intuition agrees. So some functions are going to be too complicated to graph, but there are some functions, if you see them enough, you get an idea of what the behavior is. And later on in later lessons, we're also going to explore how to use limits to actually help us graph functions. So this is what our function is going to look like, which should be familiar from the last video. And so we see that whether or not we're approaching from the left or the right, our growth is going to be uncapped towards positive infinity. So in conclusion, for this problem, the limit as x approaches 0 of f of x is infinity. But remember, we also have to state, so the limit does not exist. Because remember, our left hand and right hand limit do agree, but they don't agree on a finite value. They just agree that our growth is going to get out of control. So we should state, because it's a specific descriptor, that our limit as x approaches 0 is infinity. But we need to also remember to state that this limit actually does not exist. Alright, so I hope that these examples were helpful and gave new strategies and really made you rethink that temptation of just plugging in the value for the limit to solve it. So we should have different tools now, like maybe approaching from the right and left by using these t-charts. And also graphing is a good way to double check your intuition and double check any algebraic work you may have done. So thank you. Please leave any feedback in the comments. That'd be appreciated. And have a good day.